Let's now move um, into a discussion about why multiprocessor hardware plays a role when it comes to scheduling and why it actually makes it more complicated. Let's start discussing the concept of the role that caches have. So here we have three different organizations of CPU and memory. We have an initial one, the first one here, in which we just have two CPUs and they have some shared memory they can access. Then we have a second one in which we have the same thing, but now each CPU has also a private cache, so a smaller memory where it can keep recent data that is accessing. So, for example, a block of instructions, so that when you need to fetch the next instruction, you have already there instead of just going back and forth every time from the memory. But in practice, you can even have something like the third one, which is even more complicated. So you have both private memories, caches that are also dedicated to different CPUs, and then you have also the shared memory. This is actually how modern architectures look like. So if you assume we are in one of these setups, let's say either B or C, now you can see that you might have a process that is running on this CPU, on this CPU, the second one, this one. It issues a request for input output, so it goes into the waiting state. Now, since it was the process was running here, it probably had some data in the cache. And if the cache was not cleared, when we want to run the process again, it might actually be beneficial for its performance to get back to the same CPU, because it will find already some things in the cache. And since they are there, there is no need to go through the bus here and go back to the main memory to fetch the data. But of course, if we reschedule the process, but instead of this CPU, we send it to another CPU, not a big deal. I mean, it will still work, but since there is nothing in the cache from the previous execution, it will need to go to main memory and take stuff back to the cache. So you see that if you want to achieve better performance, you might want to try to place processes back to the same CPU they were running. But of course, everything comes with a price, okay? So if you want to do something like this, then you need at least to keep additional information about which process is being scheduled in which CPU, so that you send it back there. It's also more complicated than that, because it might be that you have a lot of free CPUs, but just the one you want, it's actually used by another process. What should you do then? Go to another one, or maybe wait a bit and see if it gets free and place again the process on the same CPU. Not important right now how you solve this in practice. It depends on how the operating system is implemented. But what I'm trying to say here is that you see that as soon as you bring in multi-core architectures and their actually placement of memories, if you want to be efficient, if you want your scheduling to perform well, then you start having a lot of challenges you don't have with a single core, single CPU architecture. Let's move to the next one. There was something more I wanted to say here. Yes, in fact, if you are familiar with C programming, you know that you can specify when you start a process, you can tell the operating system that you want this process to be pinned to a specific core. Okay, in that case, the operating system is only allowed to use that core for running the process. Okay, even if there are context switches in between. And now you can see that this is done for performance, because you know that since you always use the same core, you also have access to the same memories and caches and so on. So there are higher chances that you don't have to go to the main memory to fetch back your data, but you can use your local cache. We have other type of architectures, the non-uniform memory architectures. Okay, so inside a computer, we can have different sockets. Each socket can have its own CPU, and each CPU can have multiple physical cores. Okay, and this is what is being shown in this image. So we have 4 sockets, and each of the 4 CPUs has 4 cores. Now, within each socket, the CPUs can share their own memory, but they can also communicate with other CPUs, okay? So this is non-uniform because, as you can see, if C1 and C2 want to share some data, they can do it through their own memory. So it's faster than if C1 here and C1 here need to share something, because then they need inter-socket communication. And this is another challenge. So if you want to schedule 2 threads, and you know that these have a behavior that could resemble that of a producer and a consumer, assuming you know this, then it might be more beneficial to place these 2 in cores that belong to the same socket, because then the number of memories they need to go through to communicate is smaller, and they can use their own memory. So like in the green case, than in the red one. But again, you need extra information. You need to maintain extra information about the threads and the processes if you want to do this to improve the performance of your achieved by your scheduling strategy. Okay. And of course, there is an extra challenge here, that is, how would you know that 2 threads are a producer and a consumer? If it's a general system, an interactive system, you don't know what is going to run, you might not really know this. There are specific cases in a batch system, for example. You might know what processes you are running, and you might know that many of them have this kind of relation, so you can take better decisions based on this. But in general, you wouldn't know.